All right, it is 10, so we will get started today. And we are picking up right where we left off on Wednesday. In the last topic, well, first off, we were just talking about precipitation reactions and how to write them, where you just switch the cations around in each reaction. In the new molecule you make, you ask yourself, is that soluble? And based on our solubility rules, either we have a reaction, or if nothing is soluble, we have no reaction. And then we looked at complete and net ionic equations, where we take everything that's aqueous. Remember, if you're aqueous and you're in an ionic bond, that bond will break and you'll form separate ions. Sorry, had to sneeze there. So that's a complete ionic equation. Then you look at the ions on each side of the arrow, both reactants and products. If it appears on both sides, then it's called a spectator ion. It doesn't actually do any chemistry, so we cancel it out. And whatever we're left with is what's called the net ionic equation, which is the chemistry we actually do. Then we got into acids and bases. Remember, an acid is something that when the ionic bond breaks down in water, we release H plus, while a base will release an OH. And when an acid and a base mix, you get water plus salt. So this is the last slide we left off on. And we're going to jump right into an example problem here. So we want to write the balance, molecular, and net ionic equations. And I guess we can also do the, while we're doing this, net and complete and net ionic equations. So I'll do A for us, because maybe you don't remember how to name these acids. Then I'll give you time to try B and C. So for A, the reaction is between hydrobromic acid. So remember from our naming schemes, if you see an acid with the word hydro, all that means is there's a hydrogen out in front. That's what a hydro acid is. And it's also just made out of two different elements. That's what a hydro acid is. It's diatomic. So hydrobromic, bromic, bromine, so HBr. And at this point in the class, we really need to start writing our state symbols. That is it aqueous? Is it solid? Is it liquid? Usually for this, you can assume everything's aqueous unless I specifically say so. Or if it's insoluble, then you have to use solid. Or if it's water, you have to use liquid. So we have HBr plus potassium hydroxide. So potassium is K. K has a +1 charge. Hydroxide's OH. And together, OH has a -1 charge. So that is balanced charge-wise. I can do the same thing with HBr. H is +1, Br is -1. So it's balanced charge-wise. So that's good. That's how we know what the element is. Aqueous. All right, so I'm writing the molecular equation. And what we need to do is, just like in our solubility rules, swap the cations. So we'll get KBr, again, +1, -1, so it's balanced. And we go to our solubility rules table, and we see K is soluble, no exceptions, so that's aqueous. Then we'll make H2O. H2O is always a liquid, unless otherwise stated in the problem. We'll look at that. It's balanced with all the molecules. Since we didn't put any coefficients, it's all balanced. So that's the molecular equation. Now the complete ionic equation, again, anything that is aqueous, just break apart. make sure you put the charge. So HBr breaks apart into H plus aqueous, Br minus aqueous, then K plus aqueous plus OH minus aqueous goes to K plus aqueous, Br minus aqueous. Then anything that's a solid, liquid, or gas, you don't break up. So that's H2O liquid. And then for the net, we need to take the complete and cross out anything that's on the arrow on both sides. So Br minus, with the Br minus gets canceled out. K plus canceled out. So our net ionic equation for this acid-base reaction is hydrogen plus OH minus makes water, which is going to be for, just about every single acid-base reaction you come across. When you mix an acid and a base, they destroy each other to make water. They're neutralizing each other. All right. So any questions on how I worked out A there? And if you don't have questions, feel free to work on B and C as well. I'm going to leave A up here as our example, and B and C, you already have these starting reactants. So let me know if you do have questions. I'm going to put up our question timer just so I can get a feel for where people are at. Otherwise, let's try to work out some acid-base problems, see if we get that. We'll do about another minute for this, and then I'll start filling out B for us. right, so hopefully you got some of the way through to at least try and be, getting in there firsthand experience of how to solve these problems. So let's tackle it. I'm going to erase A so I can have some room here. So the first thing I would do when you're new to these problems is just try and figure out what the charges of each ion would be if they were separated, because it's going to make balancing a whole lot easier. Hydrogen is always going to be +1. Since I have 2 hydrogens and SO4, and this is another thing we really need to be able to just look at, start to understand S and O are both nonmetals. So they will form a covalent bond and they're a unit. So if it's +1 and you got 2 of those, SO4 must be 2- as a unit. Calcium is going to be +2. It is in the second column, always +2. OH is always -1, and there's 2 of them. When doing this, a common mistake I will see is, like I said, I mentioned this on Wednesday, but this 2 here doesn't mean that the H's travel as a group. They are free to be independent. So you have 2 hydrogens, not a hydrogen and a hydrogen bound to each other, right? The only time you're going to travel as a unit is if you're these polyatomic anions, which would be all nonmetals. Okay, so the first thing I do is switch my cations. CaSO4 +2 -2, balance, so I don't need to mess with any coefficients. Aqueous plus H2O. It is not H2OH2, it is H2O. That's liquid, and as a balance, there needs to be a 2 here. That 2 is coming from, there's a total of 4 hydrogens, right, on the left-hand side. So 4 hydrogens on the right, and that would be balanced out. So that's my molecular. My complete, I'll do this relatively quick. So H plus, aqueous, SO4, 2- aqueous, again, splitting up anything that's aqueous, Ca 2+ aqueous. Any coefficients, or sorry, that's supposed to be a 2. Any coefficients you bring out to the front. So 2OH minus aqueous goes to Ca 2+ aqueous. SO4 2- aqueous. Anything that is not aqueous, you do not break apart. So H2O liquid. So that's your complete. Get out my red pen. What's the same on each side? Well, SO4, SO4, Ca, Ca. Our net equation is just very much like the equation for A because it's acid base. 2H plus aqueous. 2H minus aqueous makes 2 water. Liquid. Wouldn't CaSO4 be solid? I forgot to check that. Thank you very much. I was just kind of like going in on my autopilot. Very good. Something I forgot to check, and I would have got this problem wrong. That's what happens when you're on autopilot. CaSO4. Very good. So SO4 is soluble unless it pairs with calcium. So yes, that is a solid. And so I need to not break that up. And so my net is completely different. So my complete and my net are now the same thing because nothing cancels on either side of the equation. So this is a precipitation reaction and a acid-base reaction. All right. Now HCl. Well, any questions about B until I go on to C, other than my obvious, it's Friday, blunder? All right. So let me figure out the charges here for C. So +1, -1, BaOH. So OH is -1 always. I have 2 of those. So Ba is +2. Switch my cations. BaCl. Cl is soluble unless paired with these 3. Ba is not one of those. So aqueous. Then H2O liquid. Looks like we do have some questions here. So one sec, let me just do this. So Ba is +2, Cl is -1, so you need 2 there. Now I need to balance. So HCl, 1 Cl, 2 Cl. So I need to have that balanced. So now we have 4 hydrogens, 2 hydrogens right there. All right, let me get to these questions now. Why is the number before H2O? What is number before H2O and why? So the number before H2O on B is 2. And the reason for that is if we look at the balancing, right? So H, and one of the things you can do for balancing is that if you have a polyatomic anion, you can just keep that together for balancing. So we have H, SO4, CO, Ca, and O. No, the line below is that a 12. The line below that. 12. Oh. That is a 2. No. Gotcha. All right. Do you understand how it's balanced now? Do you get the whole 2, or do you want me to continue with the what I was doing over there? Yeah, that was just me. That one is out of nowhere. Okay, gotcha. Can you go over the products on the complete equation for B? Sure. So we have 2 products for B. Because when I switch my cations, I have to see what I get. So you're going to combine H and OH, right? Because I'm just switching the cations, and H and OH makes water. Then CaSO4, calcium sulfate. To determine like what the combination of each of them are, you have to just look at the charges. So H +1, OH -1, so they form 1-to-1 to form H2O. Calcium +2, SO4 -2, so they combine in a 1-to-1 ratio to make CaSO4. So that's our products for B. Yeah, H2O. The only thing that gets split are aqueous, not liquids or solids. Yeah. All right, so let me just reiterate where we're on C then. So C, what I did, again, I just figured out the charges of each molecule or each atom. Ba +2, OH -1, H +1, Cl -1. Switch the ions, switch the cations. So Ba is +2, so Cl, we need 2 of those molecules because Cl is only -1. Because remember, this whole thing has to be neutral charge. So that would be BaCl2. And that's really how you can figure out like the chart or what is the structure of any ionic compound. You need to look at the charges like we're doing here. Then water, we had H2O. And to balance this, since I have Cl2 here, I needed 2 Cl on the left. And then when I look at my total hydrogens, I had 4 hydrogens on the left, only 2 on the right. So that's why I put the 2 in front, and the oxygens balance out as well. So that is my molecular equation. So complete, break apart anything that says AQ in it. So 2H plus. And so I don't know if we had this yet, but this 2 distributes to everything when you break it apart. So not only is it 2H plus, it's 2Cl minus as well, plus Ba 2 plus aqueous, plus OH -1 aqueous, And that goes to, sorry, there's 2. Always got to distribute the 2. Ba plus 2 aqueous. Now, again, a common mistake I'll see is people will leave this as Cl2. No, you always need to bring the 2 out in front. 2Cl minus aqueous, 2H2O liquid. And then to go to the net, you just need to see what's the same on each side of the equation. So 2Cl, 2Cl, Ba, Ba. And then you get our acid equation, 2H plus aqueous plus 2OH minus aqueous makes 2 water molecules liquid. So that is your net equation. Again, it's the classic acid-base equation where you make water. Any questions about that while I let my dog out before she starts going insane? All right, so if there is no questions about that, we'll move on then. The next thing we're going to look at is something called a titration. Those of you taking lab, you're going to run into this concept soon if you haven't already. So it is important to try and get this idea down. Because every time we do this lab, I'm always asked, do the students know this? And then I say, yeah, we went over it. And then I hear back next week, they didn't remember anything. I have to reteach it. So let's try to go over this. So what an acid-base titration is you have, let's say, an acid, but you don't know what the concentration of that acid is. So I give you like a flask of acid and I say, I don't know what the concentration of this is. Like, I don't know how many moles of acid are in here. So what I want you to do is to take base of known concentration. You know what the concentration of this base is, and you're going to add enough base until you have converted all of the starting acid into water. Because then we can do a calculation, which I'll show you in a second, to figure out what was the starting concentration of this acid. And in a lab setting, what we have to do to monitor this reaction is use what's called an indicator. An indicator is a molecule that changes color at different pHs. So we have an indicator that changes to pink at like a pH roughly, I forget what it is, but let's say it's roughly around 6. And so at an acid, when you have nothing but acid in a flash, your pH is really low. You know, you're talking about a pH maybe like 0 to 1. You add enough base until it's neutralized. And when it's neutralized, it will go higher and higher. And generally you stop once you see pink. Because once you see pink, that means your acid is pretty much all gone at that point. And then we can back calculate to figure out, okay, what is the concentration of acid you started with? So that's titrations in a nutshell, what you do in a titration. Let's actually go over the calculations of how to work this, how to work a titration calculation. So I'm going to do and I'm going to draw the picture for us because I think pictures really help here. So I have a flask. This flask has the acid H2SO4. And I know there's 30 mils of this, but I don't know the concentration. I don't know the molarity of this acid. So to figure that out, I'm going to add a base of known concentration. So I have NaOH. And this NaOH has 1.5 moles of NaOH per liter. That's the molarity. That's what big M stands for. And I did this experiment. And in total, I added 25.23 milliliters of NaOH to neutralize my H2SO4. Therefore, what is the concentration of H2SO4? Okay, so the first time you see titration problems, I'm sure they're super confusing, don't even know where to begin. So let's try to break this down in steps. So your step 1, write a balanced equation. That's what you should always do for a titration. And we just did this on the last problem for A. So, and actually B and C. So we have H2SO4 aqueous plus NaOH aqueous. Now we have to figure out what we're going to make. So H is +1, SO4 is -2. Na is +1 because it's on the first column. OH is -1. So we need to switch our cations. So the first product we're going to make is NaSO4 aqueous. We need to look at the charges again. So Na is +1. SO4 is -2. So we need 2 sodiums to balance out the charges. So Na2SO4. And our other product is going to be H2O liquid. Now we have to balance out the equation. So 2 sodiums on the right, 1 sodium on the left. So I need a 2 here. Now 4 hydrogens on the left, 2 hydrogens on the right. So I need a 2 here. And then everything should be balanced. Right, so that's our step 1, write a balanced equation. Before I move on, any questions about like writing the balance equation? All right, so after writing the balance equation, what we're doing here is solution stoichiometry. And we already talked about this concept. But it's solution stoichiometry. So step 2, how many moles of NaOH did I add? How many moles of NaOH reacted with my H2SO4? So that's relatively easy to figure out because we have a molarity and we have a volume. So step 2 is moles of H2SO4. So I have 0.150 moles of NaOH per 1 liter of NaOH. And 25.23 milliliters is 0.02523 liters. You just take this milliliters divided by 1,000 to get the liters. So I take this, multiply it by 0.02523, and get out my handy calculator, aka my phone. Oh, it slowly boots up. There it is, 0.15 times 0.02523. And the number of moles of NaOH I added was 0.00378. Why did you move the decimal in the 25.23? Because I needed to get it into liters, because I'm trying to figure out moles of NaOH. And right now I have molarity of NaOH, which is moles divided by liters. And so to cancel out the liters, right, I need to multiply molarity by liters, right? Because if we look at the train track, I have liters on the bottom. And if I multiply by liters on the top, my final unit is moles, which is what I want. So that's step 2. How many moles of NaOH should I have? Step 3. Okay, once you have that, how many moles of acid did I have? Or in this case, H2SO4. And as long as you have a balanced equation, you can figure this out. Because from our balanced equation, we see that for every 2 moles of NaOH that you have, you react with 1 mole of H2SO4. Remember, if I'm trying to switch between different compounds in my calculation, the only unit you can be in is moles. You can't be in grams, you can't be in molarity, you have to be in moles. So I'm trying to switch from moles of NaOH to moles of acid. So NaOH at the top, NaOH on the bottom, they cancel out. I'm left in a unit of H2SO4. So I take that number divided by 2. And the number of moles of H2SO4 I started with was 189 moles. So that's step 3. Questions about that until before we get to the very final part of this problem? So step 4, solve for molarity of H2SO4. Molarity is moles divided by liters. So I just told you how many moles of H2SO4 we have by figuring out the moles of sodium hydroxide. And in the very beginning of the problem, I already told you what is the volume of H2SO4 that we start with. To get molarity, remember it's moles divided by liters. So I need to take my milliliters, divide by 1,000. So let me just do that longhand. There are 1,000 milliliters in 1 liter, which is 0.0300 liters. So I take my number of moles divided by my liters of H2SO4. And I get, whoops, I want to do division, 0.03. The molarity of H2SO4 in this experiment is 0.0631 molar. Just taking my moles of H2O SO4 divided by my liters of H2SO4. All right. So questions, confusions of what I did here. Where did I lose you if I lost you? Looking at that, what didn't make sense? Getting confused with the process because it's all over the page. So let me label it then. So this was step one. That was step 2. How many moles of NaOH should I have? This is step 3. How many moles of acid did I have? This is step 4, molarity. So each one of those calculations goes to each one of the steps I wrote there in the bottom. Balancing it, figuring out moles of NaOH, going to moles of acid, going to molarity of H2SO4. All right, so try and do B. B is a little different because it's not a carbon copy of A. I'm asking you to do a similar process, but this time I want to know a volume. So I want to know how many milliliters do I need to neutralize a 30 mil sample 0.2 molar NaOH if I have 1.25 molar HCl. So this should be milliliters of HCl. This will be your final answer. So see if you can follow kind of like the logics I did here and do something similar for B. It's not going to be one-to-one. You can't follow these 4 steps exactly because we're not solving for molarity. We're solving for volume now. So it's going to be a little different, but the process is going to be 99% the same. So see if you can figure out that, at least get a couple of the steps done. So I'm gonna allow you to get your hands dirty with that. And if you have questions, confusions, you get like stuck, feel free to send me a message and we can try and work from there. So in case you're still having like trouble with like, what steps should there be, right? Let me tell you like the logic steps up here, and it's going to be very similar to what we just did. Step one never changes, right? Always write a balance equation. No matter what we're doing, you need a balance equation for any titration problem. So step one, write a balance equation. Then step two, how many moles of NaOH did I add? That's the same here. So whenever you're given in a titration problem a molarity, I guess I should just do big M plus a volume, usually you want to figure out, okay, how many moles is that? Because moles is a unit we can work in. Molarities, we can't convert between different molecules when we're just in molarity. So how many moles of NaOH did I add? So that's the same here, because NaOH in the problem we have both a volume and a molarity. 3, since we knew this is a reaction which is neutral, it's been neutralized, it's the same question. From 2, if you know how many moles of NaOH you have, and you have a balance equation, you can figure out how many moles of acid did you have in that reaction. And step 4 is going to be different for us because we're not asking for molarity in this question. We're saying solve for milliliters of HCl. So time is running short, so I think I'll work through this. I will also probably look for more practice problems on this, as this is something that people generally struggle with. Let me erase. I'm going to erase all the work for problem A, and I will do problem B in the same spot. Erase faster, please, eraser. Maybe, yeah, there we go. I'm just going to use my pen. All right. So step 1, write a balance equation. So NaOH aqueous plus HCl aqueous makes sodium hydroxide aqueous plus H2O liquid. Everything's balanced 1 to 1. You can look at the charges. Everything is +1, -1. So no need to mess with any coefficients. So that's step 1. What is my balance equation? Step 2. How many moles of NaOH did I add? Well, like I said, you can solve this if you're given a molarity and a volume, because molarity, whoops, let me get the other color out. Molarity is just moles divided by liter. So I have 0.200 moles NaOH divided by 1 liter of NaOH. That's my molarity. And to get moles, you just need to multiply it by volume. You need to cancel out the liters. Here, I'm giving 30 milliliters for every 1,000 milliliters. That's 1 liter. So that's 0.030 liters NaOH. Liters cancel out. I'm left with moles. Oh, sorry. It's supposed to be NaCl. That's a good point. I forgot to switch my ion. So it should be sodium chloride. So going from moles of NaOH, molarity of NaOH to moles of NaOH. Get out my trusty phone calculator. 0.2 times 0.03. As my dogs go. absolutely bananas. That is 0.0060 moles of NaOH. So that's step 2. Took the molarity of NaOH, multiplied by the liters to figure out moles of NaOH. Now we go to step 3. How many moles of acid do I have? Again, that comes from our balance equation. So I know how many moles of base I have. And my equation's 1-to-1. So this is relatively easy because for every 1 mole of NaOH I have, that's 1 mole of HCl. NaOH cancel. So it's this actually same number. Yep, my bad. 0.0060 moles of HCl. So all that's matched up. Now, step 4. How many mils will it take to neutralize this base? So how many mils of acid do I need? So the question is, if I have 1.25 moles of HCl for every 1 liter of HCl, how many liters contain 0.0060? So I don't know if we've done a calculation like this before, but it's just a unit conversion. That's why whenever you see big M, you need to be thinking to yourself, this is moles divided by liters. It's 1.25 moles for every 1 liter. And if you're given moles, in this case HCl, we can use molarity as our conversion unit, conversion factor, to go from moles to liters, because for every 1.25 moles of HCl I have, moles of HCl are now canceled out. I have 1 liter of HCl. So I can do that calculation. 0.0060 divided by 1.25. The number of liters of HCl that I had were 0.0048 liters of HCl. And then I just need to convert that into milliliters, because that's what the question's actually asking. For every 1 liter, I have 1,000. I didn't need to put the X there, 1,000 milliliters. So I take 0.0048 times 1,000, which is 4.8 milliliters of HCl. So I know titration problems. When you're looking at these for the first time, I'm sure your mind is exploding because there is so many moving parts. So I tried my best to like highlight what this problem is doing on a step-by-step basis. In reality, when you get really good at this, and it takes a lot of practice to do this, so don't beat yourself up if you can't quite do this yet. Once you get a lot of practice in, step 2, 3, and 4 can be all done in one calculation. But I think to begin with, for these types of problems, I think it's very nice to work them out stepwise like this, so we can actually see, what's going on at each single step of the equation or the problem. And like I said, I will find more titration problems for you to do, put those up so you can have a lot of practice on this. And hopefully after you do this a couple times, it will start to make sense. But before I let you go, is there any questions? And I realize I didn't get to the PowerPoint that I made for today. That's okay. We can make that up. But any questions that people might have about what I did here? All right. Well, I will put up a homework that will give you more practice with this. Again, hopefully with all those examples, it will start to click. And I'll let you know, I'm going to ask you a titration problem on test 2. It's 100% certain I'm going to do that. So let's get our practice in. Let's make sure we have that concept. And so when you see this type of problem on test 2, it'll be like easy, slam dunk. Takes me 2 minutes to do it because I have so much practice with it. Otherwise, if you have questions, as I said, as always, feel free to email me. Otherwise, that's what I have for you today, and I will see people on Monday. Have a good day, everyone.